waves and normal modes. Let us now consider a system which is bounded at both the ends, such as a stretched string fixed at the ends or an air column of finite length. When the wave reaches the right end, it gets reflected and begins to travel back. The left-going wave then overlaps the wave, traveling to the right. When the left-going wave reaches the left end, it gets reflected again and the newly reflected wave begins to travel to the right, overlapping the left-going wave. This process will continue and therefore very soon we have many overlapping waves which interfere with one another. Such wave patterns are called standing waves or stationary waves. We therefore have y1 as a function of x, t equals to a sine kx minus omega t, where wave traveling in the positive direction of x-axis, and y2 as a function of x, t equals to a sine kx plus omega t, where wave traveling in the negative direction of x-axis. The principle of superposition gives for the combined wave y as a function of x, t equals to y1 as a function of f, t plus y2 as a function of x, t equals to a sine kx minus omega t plus a sine kx plus omega t equals to 2a sine kx cos omega t. Note the important difference in the wave patterns discussed earlier. The terms kx and omega t appear separately, not in the combination of kx minus omega t. The quantity 2a sine kx is the amplitude of oscillation of the element of the string located at the position x. Thus, in this wave pattern, the amplitude varies from point to point, but each element of the string oscillates with the same angular frequency omega or time period. There is no phase difference between oscillation of different elements of the wave. This wave pattern is neither moving to the right nor to the left. Hence, they are called standing or stationary waves. This animation shows formation of a standing wave in the stretched string. Stationary waves arising from superposition of two harmonic waves traveling in opposite direction. Note that the position of zero displacement nodes remains fixed at all times. The position of zero amplitude are called nodes. The amplitude is 0 for values of kx, that gives sine kx equals to 0. Those values are given by kx equals to n pi for n equals to 0, 1, 2, 3 and so on. Substituting k equals to 2 pi by lambda in this equation, we get x equals to n lambda by 2 for n equals to 0, 1, 2, 3 and so on. A distance of half a wavelength separates two consecutive nodes. The point at which the amplitude is the largest are called antinodes. The amplitude has a maximum value of 2a which occurs for the values of kx, that gives modulus of sine kx equals to 1. Those values are kx equals to n plus half pi for n equals to 0, 1, 2, 3 and so on. Substituting k equals to 2 pi by lambda in this equation, we get x equals to n plus half lambda by 2 for n equals to 0, 1, 2, 3 and so on. The antinodes are separated by lambda by 2 and are located halfway between pairs of nodes. For a stretched string of length L fixed at both ends, the two ends of the string have to be nodes. If one of the ends is chosen at position x equals to 0, then the other end is x equals to L. In order that this end is a node, the length L must satisfy the condition x equals to n lambda by 2 for n equals to 0, 1, 2, 3 and so on. This condition shows that standing waves on a string of length L have restricted wavelength given by lambda equals to 2L by n for n equals to 0, 1, 2, 3 and so on. The frequencies corresponding to these wavelengths are frequency equals to Nv by 2L for n equals to 0, 1, 2, 3 and so on. The equation tells us that the natural frequencies of a string are integral multiples of the lowest frequency, frequency equals to V by 2L, which corresponds to n equals to 1. The oscillation mode with that lowest frequency is called the fundamental mode or the first harmonic. The second harmonic is the oscillation mode with n equals to 2. The third harmonic corresponds to n equals to 3 and so on. The collection of all possible mode is called the harmonic series and n is called the harmonic number. Which mode is strongly excited depends on where the string is plugged or bowed. Musical instruments like sitar and violin are designed on the principle. Here you can see images of few harmonics.